Chapter 5, Surge Protective Equipment. Next, we're going to look at some of what we call the first level or first stage of equipment protection. And this usually occurs at a lower level, in other words, the distribution level of power systems, which municipal utility, for example, in distributing power to the customers might engage this type of equipment to take care of any type of surges that might occur in the system, such as lightning or quick overvoltages as equipment gets switched around. The function of surge protective equipment is to reduce interruptions to our power service by discharging voltage surges initiated through lightning, switching, or other disturbances, and to protect maintenance personnel and the public, and to prevent or lessen damage to valuable electrical equipment. Basically, the equipment is required to be suitable to protect associated equipment by discharging voltage surges above a predetermined level, to have suitable inherent characteristics so that the voltage drop within itself during heavy current discharges will not be excessive, to reseal against operating voltage and power flow current after the surge has been discharged, and to have suitable insulation resistance to withstand operating voltage indefinitely. One of the simplest forms of surge protection is the spark gap. It will break down at a predetermined voltage, but will not usually extinguish itself. So the interruption of power current flow depends upon some current limiting device, either a fuse or regular station protective relaying or switching. Spark gaps are usually used to ensure that the voltage level at a station is below that of the apparatus with the lowest impulse voltage level. These are frequently used on a system because they usually are more economical than expensive arresters. One style of spark gap is the rod or pipe gap. These are simply two rods of sufficient size to handle the anticipated current flow without damage. One side is connected to the line, the other is connected to the ground. The gap length is adjusted to give the required impulse spark over the voltage. Horn gaps are another style of gaps that are really just a modification to the rod gap. On each rod is a horn, usually rising vertically from the rod. As these horns rise, the separation between them becomes greater. Since the arc usually rises along the horns, there is a less burning of the gap material, and since the arc length is increased, it is more easily extinguished. For some applications, the horn gap is practically self-extinguishing. Hemispherical or spherical gaps have similar characteristics. For a given value of spark over voltage, they have a smaller separation than rod gaps. Their spherical shape has a similar effect as to the horn gap in lengthening the arc and thus making the arc easier to extinguish. Ring gaps, as their name implies, these two parallel rings usually installed around suspension type insulators to protect the string from destructive arcovers. This type is usually used on 230 kV systems. And lastly, I thought I would just mention this type of gap protection. It's the distribution type, and you see a lot of these in and around distribution systems. The arresters are available in ratings from 1 to 18 kV line to ground. They are generally used to protect distribution transformers and other small distribution pieces of apparatus. A number of manufacturers include an automatic disconnecting device that will break the ground connection to the arrestor if it fails. Although a lot of them are being used, experience has shown that these devices are not very reliable, as it is frequently the case where fuses will operate to clear the fault before these stylet gaps have a chance to operate it. Nevertheless, they are used, and you see them all around the distribution system, and their function is really to try and protect surges on the system. Experience has taught us that equipment connected directly to a power source without fusing sustains major damage when short circuits develop within it. In addition, the faulty equipment connected directly to a power system imperils other equipment to which it is connected and the stability of the whole system at large. Fuses reduce this hazard. By definition, a fuse is an overcurrent protective device with a circuit opening member heated and destroyed by the current passing through it. The purpose of a fuse is it is used to open the circuit when the magnitude and duration of the fault current exceeds predetermined values. As can be seen here, there are numerous types of fuses out there, all designed for different purposes. There's very different amperage ratings on them, there's different interrupting capacities in them, and there is also different voltage ratings. What we're going to look at in the next few slides are the fuses that are attached to the low voltage distribution systems. This is a typical distribution type fuse system. Generally speaking, they're all pretty much the same, and the construction is very similar to all of them. This one in particular has a fuse mounting. As you can see here, it's bolted to the pole to connect from the line to the device that's being fused, such as a distribution transformer here. The fuse holder itself is located here, and fuse links go inside the fuse holder. Line terminations are made on each end of the insulator. Fuse fittings consist of a hinge and a jaw, and when the fuse blows, the fuse element releases the jaw, and the jaw falls open, and you can tell that the fuse is blown because the fuse holder has swung down, and you can see it quite visibly from the roadside. The fuse holder usually consists of as I said, a porcelain tube or some fiberglass tubing which may be empty or contain solids or liquids to assist in the arc extinction. Ferrules are usually attached to the fuse element that goes inside to make the connection to the outer circuits a lot easier. The fuse link, the fusible element connecting the two line terminals of the fuse holder, is usually a composition of material that depends on the speed required, the interrupting capacity, and is made up of several alloys or materials that the manufacturer can offer the user. The fuse element is constructed in various ways to use different methods for breaking the arc in the case of when it's interrupting the overload situation. Mechanical separation, essentially this is just a rapid separation of the parts of the fuse after it is melted. This is commonly accomplished by maintaining a spring tension on the fuse element. Arc treatment, in addition to the mechanical separation, gaseous discharge initiated by the heat of the arc is used to sometimes cool the arc, to deionize it, and to expel the arc products from the fuse holder. In certain cases, you can have liquid cooling, and it is used for high rupturing capacity fuses to cool and de-energize the arc. Current limiting is a feature in some of the high interrupting capacity fuses where fast fusing elements blow, inserting a high resistance to prevent the full buildup of a short circuit current. The greater majority of fuses can be divided into three categories. There's the gaseous discharge or expulsion fuses. There are high rupturing, interrupting capacity type fuses, which we call liquid fuses. And we have fuses that are designed to limit the current when blowing, called basically current limiting type fuses. The expulsion fuse, or the boric acid fuse, has a lining inside the fuse holder, which is essentially boric acid. After the fuse link melts, an arc forms. The heat of the arc produces gases from the lining material, and the gases formed at high pressure carry the arc and the arc products out of the holder. Extending the arc increases the resistance, and the arc has less tendency to restrike. The blowing fuse produces quite a loud report or a noise, and if this is objectionable in highly residential areas, a muffler can be used to reduce the noise and to catch the conducting arc products. One type of indication that the fuse has blown is the dropout type fuse holder. When the fuse blows, a catch is released on the upper end of the jaw, allowing the upper end to fall due to gravity. The spent fuse holder pivots on a hinge at the bottom end of the fuse holder and remains suspended from it, a clear indication that the fuse is blown and a circuit is open, and it's quite visible from the road. Liquid fuses contain a liquid, an arc extinguishing liquid inside the glass tube. The fuse link consists of a fusible element and a small strain wire of steel in parallel and held in tension. The strain wire prevents the strain from being applied to the fuse link. However, when the fuse link melts, the steel wire also melts. The arc is drawn in the liquid, which cools and deionizes it as it is extended by the spring. Arc extinction is very fast, and heavy currents can be broken with this type of a fuse. The quartz fuse consists of a glass or ceramic holder, and the fuse link consists of one or more fuse wires wrapped around a heat-resisting core and surrounded by quartz granules. The fuse wires melt on the rising current wave, and silver vapor is expelled into the surrounding quartz granules and condensed back into microscopic globules of silver. The arc current continues to flow between the globules, heating and melting the quartz, which forms a non-conducting solid. The arc is quenched gradually as the solids form. Its resistance progressively increases, and the arc current correspondingly decreases. The gradual extinction of the arc prevents excessive voltage surges, yet the whole action takes place in a half a cycle. There is no noise, no discharge, and negligible gas pressure during the arc interruption. A fine target wire that melts when the fuse melts burns a gas-producing chemical to push out the target disc at the bottom of the fuse holder, so it can be identified as being blown by just looking up at the fuse holder. This table denotes the type of fuse and its interrupting capacity in amperes and its use in the various systems out there. Expulsion or cable type link fuses have the lowest rating of about 6,000 amps, and it's used primarily in distribution stations where short kVA is low. Liquid type fuses interrupt about 10,000 amperes. Boric acid will take on 40,000 interrupting amperes capacity. And again, they're used in distribution stations where short kVA is higher than the expulsion type fuses experience. Quartz fuses are the highest, have the highest interrupting capacity, up to 60,000 amps. And potential transformer fuses or small equipment type fuses, these are expensive fuses, but they're protecting expensive type equipment. A time current curve, or a TCC, plots the interrupting time of an overcurrent device based on a given current level. These curves are provided by the manufacturer of electrical overcurrent interrupting devices such as fuses and circuit breakers. The shape of the curve is dictated by both the physical construction of the device as well as the settings that are selected in the case of circuit breakers. The time current curves of a device gradually show the response of the device to various levels of overcurrent. The curve allows the power system engineer to graphically represent the selective coordination of overcurrent devices in an electrical system. The average curve shows the average performance of a fuse link. However, where coordination is critical, the maximum clearance and the minimal melting time times of the fuse must be used instead of the average values. Minimum melting time curves can be obtained from the average curve by reducing the value by 10% if it's not given. And the maximum clearing time curve can be obtained also from the average by increasing the values by 10% if, again, they're not given. Generally, all three curves can be obtained from the fuse manufacturer. Now, modern power systems design software packages such as Easy Power, SKM Power Tools, and ETAP, and there's many more out there, contain graphical libraries of curves to allow the ability to plot, analyze, and print the curves with minimal effort compared to the previous methods used where coordinating fuses had to be done on graph paper. Let's go again. The one-line diagram and TCC plot shown here is a typical or hypothetical industrial power system. There is a utility delivery point with power supplied at a medium voltage level, in this case 4160 volts, which feeds the primary side of a 2.5 MVA power transformer through a medium voltage fuse containing an E-class type fuse. The 480 volt secondary side of the transformer feeds a piece of low voltage power switchgear, utilizing draw-out low voltage power circuit breakers for the main and feeder circuits. Interpreting the damage curves is fairly straightforward. Operating conditions, overcurrent protection, must be kept to the left of the damage curves to guarantee no permanent damage is done to the transformer or cables in question. The TCC diagram shown plots the interrupting response time of a current interrupting device versus time. Current is shown on the horizontal axis using a logarithmic scale and is plotted in amps. Time is shown on the vertical axis using, again, a logarithmic scale and is plotted in seconds. The light blue curve is a switchgear feeder circuit breaker curve. The violet curve is the switchgear main circuit breaker curve. The orangish, I call it orangish, type curve is the transformer primary fuse curve. The yellow curves shown here are the transformer damage curves, and the green curves are the cable damage curves. Operating conditions to the right of the damage curve subject the device in question to currents that can cause permanent or irreversible damage, a shortened lifespan, and possible catastrophic failure. Therefore, the overcurrent and circuit breaker coordination schemes must take this into account during the initial design phase. There are two transformer damage curves shown in yellow. One is dashed, the other is solid. The solid damage curve is unbalanced and takes into account a derating factor for the transformer winding type and fault type. The dashed damage curve is the 100% rating curve with no derating consideration. The transformer inrush current is also plotted as a single point on the TCC diagram. Again, as part of the initial design, the transformer inrush current must be to the left of the transformer primary fuse curve, otherwise the fuse will open when the transformer is initially energized. These differences in the unbalanced and 100% damaged curves can be mitigated with additional protective relaying, allowing 100% curves to be used for power system design without the risk of transformer damage. There are three cable damage curves shown in green. There is one curve for each cable represented on the one-line diagram. As part of the initial design, the overcurrent interrupting device must limit the fault current to the left of the damage curve to prevent permanent damage. The damage curves for the cables are independent on size, insulation type, and raceway configuration. A recloser is an overcurrent protection device. It is a self-contained overcurrent device for automatically interrupting and reclosing a distribution circuit or feeder. It has a predetermined sequence of operating and reclosing followed by a lockout. The recloser may be preset to have up to 4 operations before lockout, and those operations can be any combination of fast or instantaneous or retarded in time trips. They are usually pole mounted with lockable control box near the ground level for operators to work on them. These devices are designed primarily to try to burn off any type of natural branch that might touch the feeder momentarily during the operation, and it would allow the feeder to reclose back in and not have to have somebody come out and service the feeder in order to put it back in service. However, if the branch or if the fault is more of a permanent nature, then the device will go to a lockout position, and the operators or a lineman will have to come out and clear the fault and reset the recloser manually. The fast or instantaneous operation of the recloser will de-energize the line before downstream fuses on the load side are blown, and therefore provide an opportunity for a transient fault to clear, as I've said. And it would then completely restore the operation of the feeder. The timed operations allow for the fault current to flow through the downstream load side fuses for sufficient time, or to give them sufficient time to operate, and therefore limit the isolation required to clear the fault. If a recloser goes through only part of its cycle, short of the lockout, it resets itself automatically within 1 to 1.5 minutes. A locked out recloser must be reclosed manual, and it is usually located immediately off the secondary circuits of the distribution station transformer. This will show the operation of a recloser going through its 4 cycle stages to lock out. The initial state of the recloser just prior to the fault shown here as red, indicating that the recloser is in a closed position. Upon a fault happening or a tree branch touching the feeder circuit or a fault on the feeder circuit, the recloser will trip under overcurrent conditions, and it will attempt to re-energize the circuit right after, and it'll attempt to reclose once. If the fault is still on the feeder circuit as indicated, then the recloser will trip again, and it'll attempt to reclose another time, hoping this time that possibly the branch has burned off, or the fault could be temporary and has cleared, or downstream fuses could blow, giving the circuit a chance to clear down line and maintain at least partial service to the customers. If the fault is still on the line, the recloser will then trip again, and it will try to reclose one more time. However, this time, if the fault is still present, the recloser will open and lock out, and it will require a manual reset before it's back into service. This ends Chapter 5.